I think it is better to continue from this slide. So the design objective of modern aircraft exhaust nozzle are: one is efficient expansion of the engine gas to the ambient pressure. That's what we call an optimal expansion of the nozzle. The second is low installation drag. And the third is low noise, that acoustic controlled nozzle design. Low cooling requirements. The thermal ablative materials should be there on that. That is related to low cooling. Efficient thrust reversing capability. When we want to reverse the thrust, that means to decelerate aircraft from during landing, thrust reversing is required. So efficient thrust reversing capability is required. Efficient thrust vectoring related with the direction change, the aircraft direction change. So efficient thrust vectoring capability is another requirement. And low observability for radar detection. Okay, thermal and infrared signatures. And lightweight material. The material should be high temperature resistance, lightweight material is required, and low cost manufacturing of the exhaust nozzle. So that are the requirements. Okay. So based on that, what is that gross thrust? The nose contributes to engine thrust, which is called gross thrust, and it comprises two terms, which are the momentum thrust and the pressure thrust components. So the first part indicates the momentum thrust as the exit of the nozzle, and the pressure thrust, the exit pressure minus the ambient pressure times the exit area. So the gross thrust of the nozzle is maximized when it is operated as fully expanded, that is in the optimal expansion condition. So a nozzle is fully expanded when the static pressure in the exhaust plane and the ambient static pressure are the same. That in P9 is equal to P0. That is what we call optimal expansion or maximized expansion. Now, the nozzle adiabatic efficiency is one of the things which we need. So the ratio of actual kinetic energy at the nozzle exit to the ideal kinetic energy for an isentropic expansion in the nozzle is defined as the nozzle adiabatic efficiency. So mu n indicates the nozzle adiabatic efficiency. And we can obtain this result directly from the TS diagram. Okay, TS diagram is there. Okay, T9S. Okay, T9 is there. T7, which is equal to T9. So in the temperature, which shows constant temperature condition here. So here we relate it with the what you call that, the enthalpy. Okay, the enthalpy, the total enthalpy at 0.7 in our previous representation of the aircraft engine sections. So total enthalpy at 7 minus total enthalpy at 9 over total enthalpy at 7 minus total enthalpy at 9s. 9s is given here. So this diagram, this curve indicates the P9, the pressure at 0.9, that is exit pressure condition. Another curve is here. Total pressure at 7 here. Total pressure at 9 is here. Okay, so these are represented, and the kinetic energy per specific heat at constant pressure is here for the exit condition. For S condition here, we have S condition and 9 condition. So kinetic energy of per Cp is given here. Okay, so this one is the S condition is greater than the exit condition. So that is related with V9 square over 2 divided by V9S over 2. So 2 by 2 you have left V9 square over Vs. So we can write it like this. So which is equals to V9 square over Vs square. So that is the adiabatic efficiency. Now, the fraction of the gas thermal energy that is not converted into direct kinetic energy as the exit plane of the nozzle is dissipated into heat and boundary layers and across the shock. The actual exhaust gas has higher exit static temperature than the exhaust gas emerging from the isentropic nozzle. That means T9 is greater than T9S. Okay. This behavior are best described using a TS diagram, as we have discussed it here. TS diagram describes this phenomena. Okay. I think let me remove this thing. ወደሚቀጥለው ገጽ እየሄደ ስለሚያስቸግር ኦኬ ያ and nozzle total pressure ratio, that is pi n, is the total pressure ratio. That is PT9 over PT7 is the nozzle total pressure ratio. So this parameter is a direct measure of flow reversibility. That is due to the friction and shock in the nozzle. Again, just recalling our previous chapter also, delta S over R, which is equal to minus of ln of PT9 over PT7. So taking 2 points, 9 and 7, what we have, delta S, the entropy over gas constant R is equals to ln of PT9 over pressure at total at 7. Another is the nozzle pressure ratio, NPR, which is equal to PT7 over P naught. So this is the ambient condition and this is the total. Pressure total 7 over pressure ambient. So this pressure signifies the nozzle flow expansion potential, which is from the stagnation or total state at 7 to the ambient static state at 0. And P naught is ambient pressure, and nozzle pressure ratio is strong function of altitude, demanding higher area expansion ratio of the nozzle. So the critical pressure ratio, NPR critical, is lead to sonic throat with P9 is equal to P8, which is equal to P ambient. When this happens, this is optimal expansion condition actually. For a convergent nozzle, it may minimize nozzle pressure ratio. So PT8 is P8. This PT8 is the stagnation condition or the total condition, which is equal to P8 times 1 plus gamma minus 1 over 2 M8 squared. Maybe we can express this as the temperature, okay, temperature ratio. Anyways, so the power of gamma over gamma minus 1. That leads us, because P8 is equal to P naught, so that P naught times gamma plus 1 over 2 the power of gamma over gamma minus 1. So in this case, M8 is the one that is sonic condition. If it is 1, you can arrange this. What you can get is gamma plus 1 over 2 only. So by introducing total pressure loss from the nozzle inlet to the throat, we recall PT7 to P naught is equal to the NP R critical. Okay, the nozzle pressure ratio, the critical nozzle pressure ratio, which is equals to 1 over pi Cn times gamma plus 1 over 2 the whole gamma over gamma. So that is, so the pi Cn is the convergent nozzle total pressure ratio, which we described here, Pt7 over P naught. Okay, Pt7 over P naught is that. So observing this figure, the above equation for different gas temperature and composition and loss parameters, we can show the convergent divergent nozzle condition. So you see the NPR critical is in the vertical axis from 1.8 up to 2, and the pressure ratio or the critical nozzle pressure ratio is already given here from 0.95 to up to 1 here, and the gamma values for 1.4, for 1.33, for 1.3, 1.25. So this is different gamma value for hot gas. So 7 is here, the total stagnation condition. 9 is as the exit. Okay, so, and atmospheric condition is here. So that is dominated by jet boundary condition. This is center line actually. It is center line here. So at 0.9, Mach 9 is equal to Mach 8, which is 1. Pressure at 9 is equal to pressure at 8, which is equal to pressure naught, ambient pressure. Okay, that is considered here. So we can find different values for different composition. Another thing is the high pressure in the jet at the exit plane centered expansion waves at the nozzle exit cause a flow deflection, okay, with subsequent shock wave formation. So here you can observe expansion wave, shock wave, jet boundary. Okay, for example, the one here which you observe at the boundaries are the jet boundaries. Here it is jet boundary also. These are called jet boundaries. The one with solid line indicates shock wave. Solid line here, shock wave. This is shock wave also. These are different shock waves produced. And you can observe another expansion waves. Okay, dotted lines indicates expansion waves. So that is happen in the convergent nozzle. Okay, so the convergent nozzle, which is under expanded convergent nozzle with periodic shock cell in its exit fluid. So we have two figures of merits for the adiabatic nozzle. One is mu n, and another is pi n, which we already defined them. So our mu n is this one. Mu n is the nozzle adiabatic efficiency. Okay, nozzle adiabatic efficiency is mu n. Another is the total pressure ratio, pi n. Pi n critical, this another is pi n critical here. So pi n and mu n are the two important figures of merits of adiabatic nozzle. Okay, and for the condition on which optimally expanded condition, P9 is equal to P naught, that is optimally expansion condition, we can relate those parameters with nozzle pressure ratios. Okay, here mu n is equals to nozzle pressure ratio times the P naught or P9. So this is 1 now. For P9 is equal to P9, P1 naught, it is 1. Here also 1. So relations are given in this equation. Okay. This diagram indicates the nozzle adiabatic efficiency versus nozzle total pressure ratio, pi n versus mu n, which are the two merits of figure of the adiabatic nozzle. Okay, and also for different nozzle pressure ratio condition. When pressure ratio is 2, 5, 10, 20, what happened? Different plots are there. Okay. Convergent nozzle or D-level nozzle is one of an important nozzle type. So when do we choose this convergent divergent nozzle? That is type of question. Why we are hesitating to ask that? Because it is added weight. It is heavier than other nozzle types, and also complexity also there, geometric complexity. Okay, so when we choose this, we have reason to choose this. So in order to respond this answer, we have to check some parameters. Okay, based on that, the selection criteria will be clear for us. So let's assume the adiabatic and reversible flow, which is what you call isentropic flow. The expansion process in the convergent divergent nozzle is given with the flow velocity at the exit, which is equals to radical of 2 times of T8 times 1 minus T9 over the total stagnation temperature T9, and which can be rewritten as 2 times H, because temperature and pressure are related by this kind of relation. How we can relate temperature and pressure? Okay, let me write. Okay. So we are familiar with this formula, P9 over PT9. PT9 is equals to what? T9 over TT9, the power of gamma over gamma minus 1. So we can substitute that immediately by substituting the pressure part to the temperature. What we can get is this equation. And the next equation is just because P9 is equal to P naught, so that we can substitute. And PT9 is equal to PT7. So substitute it, and finally what we get, this equation. Okay. So that is exit pressure. Exit pressure is defined in terms of enthalpy, in terms of ambient pressure, and in terms of the internal pressure. So the gross thrust of perfectly expanded nozzle is what? It is the momentum term only, because P9 and the P0 are equal, so that the pressure thrust part V come out. Only the gross thrust of convergent divergent nozzle, optimally expanded convergent divergent nozzle, is the momentum term only. And so at point Mach is equals to 1, that is choking point. The flow becomes choked. For all nozzle pressure ratios beyond the critical, that means the nozzle pressure ratio of roughly 2. Therefore, the G convergent nozzle is the sum of momentum and the pressure term, but which is represented with this kind of relation. So finally, what we can get is m.9, the mass flow rate at exit, velocity exit, the whole times 1 plus 1 minus the pressure ratio over gamma Mach 9 square. So that is the final relation for the gross thrust. I think እዚህ ጋር ዛሬ ቢበቃንስ? ሄሎ
እሺ ዶክተር። አዎ በቂ ነው ዶክተር።
በቃ እዚህ ጋር ይበቃናል። ማቴሪያል ልክላችሁና ቀሪውን ደግሞ አንድ ጊዜ እንደዚሁ በኦንላይን እንጨርሳለን። ይሄኛው
በጣም አሪፍ ነው፣ ደስ ይላል።
እሺ ኦኬ። እሺ መልካም አዳር።
እሺ መልካም